Okay, so I just wanted to do a short video that would complete the material from chapter 4. You did have a pretty involved video on perusal that helped you see how we calculate the expression for radial or centripetal acceleration. So hopefully you watched that. But we're just going to do a little bit more, just talk a little bit more about it in these slides. So we learned when we started talking about two-dimensional motion that we have to consider that acceleration can be caused by simply a change in direction of the velocity. So we talk about the phenomena when an object is traveling in a circle with a constant speed. We call that uniform circular motion because of the constant speed and that it's going in a circle. But if we look at this picture, we see that all the velocity vectors are obviously pointing in different directions. So an object staying in a circular path has to constantly change direction. And because of that, we realize that there's an acceleration that's involved, and we call that centripetal acceleration. Sort of confusing the issue. Most of the time, it's labeled as radial acceleration, so the two things are interchangeable. That is, centripetal acceleration and radial acceleration are the same thing. In the video you watched, you learned that the way that we calculate the radial acceleration is that it's equal to v squared over r. This is something that is going to come up throughout this class because there will be often situations where we have something traveling either in a circular path or at least part of its path can be approximated by a circle. Now, there is also the possibility as an object travels in a circle, it might actually also be increasing or decreasing its speed. And so that means there can also be a parallel acceleration, that is, an acceleration that is parallel to the velocity vector, which is responsible for a change in speed. And so we end up with two different accelerations. We have this tangential acceleration, and this is due to a change in speed. And then we also have the centripetal acceleration, which is due to a change in direction. These two add together to give our net acceleration. So they're simply two perpendicular vectors that add to give the total acceleration, which of course is going to be at an angle to either one of them. So we have to keep in mind that when an object goes in a curved or a circular path, we have the possibility of both tangential acceleration and centripetal acceleration. Here's another picture showing those two different types of acceleration. This is the tangential. Here, they labeled it as centripetal acceleration and then the total acceleration. Because of the fact that those two accelerations are perpendicular to each other, we can treat them as the components of the total acceleration. So let's look at some questions. So in the first question, we're told a roller coaster moves around in a vertical circle. At the bottom of the circle, the car experiences 4 times as much radial acceleration as the top. So the A at the top, if we multiply that by 4, would give us the acceleration at the bottom. We know that the acceleration we're talking about is expressed as v squared over r, but the r doesn't change. So the increase in the acceleration is due to an increase in the velocity. If A increases by 4 times, the velocity will increase by 2 times because of the fact that it's squared. So when the velocity at the bottom of this roller coaster must be 4 times as big as it was at the top in order to give 4 times greater a centripetal acceleration. So that's question. That's answer is B. Here we have another place where we're going to compare things. If you drive in a race car around a circular race track of radius 100 meters at a constant speed of 100 kilometers per hour. So then we're going to talk about going a different circular track, has a radius of 200 meters and the speed of 200 kilometers per hour. So we can actually just work with these numbers as they are, because and this one is the kilometers per hour, because we're using A as V squared over R. Because we're just trying to compare the two, we're not really doing a calculation, so we're just gonna keep them in the speed in kilometers per hour, because it's just gonna be a little bit easier. Changing them into new units is not gonna change our results. So the first track has a radius of 100 meters. The car's going 100 kilometers per hour. So we have 100 squared. So 100 squared is 10,000. And we get rid of that. And so this is about 100. It's not really in good units, but this is what we're measuring. In the second one, we have 200 kilometers per hour. So we'll take that and square it, and the radius is 200. So we get 2. And that's kind of interesting, because we ended up, in this case, the first one, the ratio of the two things gave us 100, but even though, because of the radius, I made a big mistake there. It should be a 4, and then this gives me 200. So we actually saw that because the radius of the track increased from track 1 to track 2, and the speed increased by a factor of 2. They didn't cancel each other out because the speed was squared, and so we ended up with a centripetal acceleration that was twice as great. Sorry for the mistake, but hopefully that makes sense. And finally, we're going to look at a problem where we are going to look at the Earth and think about the centripetal or radial acceleration of an object on the Earth. So we're told that the radius is 6,380 kilometers. I'm going to change that into meters, and 6.38 times 10 to the 6 meters. And we're saying it rotates once in 24 hours. That's actually the period. And we're going to use capital T to denote the period of its motion, which is the amount of time it takes to go through a repetitive motion once. You're going to see that this is a common way that we denote period in physics. So we have, let's find the radial acceleration for that object. So the period, let's go to this. The radial acceleration is going to be v squared over r. How do we find v? The v is the distance that the object travels on the equator, which would be 2 pi r, and then over the period. So that's going to be 2 pi times 6.38 times 10 to the 6, and then over 24 hours, but that's not good. We don't like those units. We need it in seconds, so 1 hour is 3,600 seconds. And so we're going to get a velocity of 464 meters per second. So wow, that's how fast you're going when the Earth is rotating. So we have 464, square it, over the radius, 6.38 times 10 to the third, and we have an acceleration of 3.32 times 10 to the minus 2 meters per second. That's really small. we want to express it in terms of g. We would take this 3.38 times 10 to the minus 2 divided by 9.8. And that number will tell us how many times it is g. Sorry, this is a 2. And that's 3.39 times 10 to the minus 3g. So it's like 3/1000th of a acceleration of gravity. So we're here that if, in the second part, if this acceleration is greater than g, objects would fly off of the Earth's surface. It's basically that centripetal acceleration would be sort of would undo the gravitational effect of pulling things in. So we want to say, well, when would that happen? Let's set the radial acceleration equal to g, because that's when the transition is going to happen. That's equal to v squared over r. We're going to see how fast something has to move in order to make that happen. So that speed that the objects would have to move at would be 7,907 meters per second. Now we want to figure out what the period is of that motion. This would be given by 2 pi, we're going to use this, the radius over the period. So we can say, find the period by rearranging this. And we find the period to be 5,069.8 seconds. This doesn't make any sense to us, or like it's not that meaningful. So let's change it into hours. There's 3,600 seconds in 1 hour. And we find that that gives us a period of 1.4 hours. That's really fast. So if the Earth rotated once every 1.4 hours, you would fly off the face of the Earth.